What if I told you that somewhere out there, hidden in the fabric of the universe, there's a shortcut, a tunnel cutting through space and time itself, a passage so powerful it could take us from one corner of the cosmos to another in the blink of an eye? This isn't science fiction anymore. Wormholes, those mysterious cosmic doorways, might just be the key to humanity's greatest leap, the first real journey beyond the stars. And today, we're diving deep into the theories that could make it possible. Think about it, for centuries we've stared up at the night sky, dreaming of what lies beyond. The stars have always felt just out of reach, separated by unimaginable distances. But wormholes change everything. These hypothetical bridges, predicted by Einstein's equations, could bend the rules of physics as we know them. Picture stepping through a doorway and emerging in another galaxy or even another time. It sounds impossible, yet some of the brightest minds in science believe it might not be. From exotic matter to quantum fluctuations, from black holes to cosmic strings, there are at least 30 compelling theories about how we might one day crack the code of wormhole travel. And that's exactly what we're exploring today. What would it take to build a stable wormhole? Could they already exist, hidden in the depths of space? And if we ever found one, what would we discover on the other side? Buckle up, because we're about to journey through the most mind-bending ideas in astrophysics, from the wildly speculative to the shockingly plausible. This isn't just about science, it's about the future of humanity's greatest adventure. So let's dive in, because the universe's first wormhole might be closer than we think. The idea of wormholes didn't just spring from science fiction, it emerged from the brilliant mind of Albert Einstein himself. Along with physicist Nathan Rosen, he proposed what we now call Einstein-Rosen Bridges, the first serious scientific framework for how these cosmic shortcuts might exist. Picture spacetime not as a rigid stage but as a stretchy fabric, warped by massive objects like stars and black holes. Now imagine pinching two distant points of that fabric together until they touch, creating a tunnel connecting them. That's the essence of an Einstein-Rosen bridge, a theoretical passage through the very geometry of the universe. The math behind it is rooted in Einstein's general theory of relativity, which describes gravity as the bending of spacetime. Under extreme conditions, like those near a black hole, the equations suggest spacetime could fold so intensely that it forms a bridge between two separate locations. Think of it like punching a hole through a sheet of paper and connecting one side to another, except here, the paper is the fabric of reality, but there's a catch. Traditional Einstein-Rosen bridges would be incredibly unstable. They'd snap shut the moment anything tried to pass through, crushed by the immense gravitational forces. That's why some scientists argue these bridges might be more like cosmic mirages, mathematically possible but physically impractical for travel. Yet this theory remains foundational because it opened the door to a radical idea: spacetime isn't fixed. It can twist, tear, and reconnect in ways that defy our everyday experience. Later researchers would build on Einstein and Rosen's work, proposing exotic solutions like negative energy or quantum tricks to stabilize these tunnels. But without their pioneering insight, we might never have dared to dream of shortcuts across the cosmos. So while an Einstein-Rosen bridge might not be your ticket to another galaxy, it's the reason we're even having this conversation, proof that the universe's greatest secrets often hide in plain sight, written in the language of mathematics. But what if we could stop a wormhole from collapsing long enough to actually travel through it? That's where the concept of negative energy comes in, a bizarre ingredient that might just hold the door open. Think of it like trying to keep a tunnel from caving in by propping it up with something stronger than gravity itself. The problem is, gravity always wins. Unless we find a way to fight back with something even stranger. Negative energy, or more precisely, negative mass, is the kind of thing that sounds impossible at first glance. In everyday life, everything we interact with, from planets to people, has positive mass. It's what makes apples fall to the ground and keeps us anchored to Earth. But according to some solutions in general relativity, a stable wormhole would need a form of matter that does the exact opposite, something with a gravitational repulsion, pushing space-time outward instead of pulling it inward. Picture blowing air into a balloon to keep it from deflating. Negative energy would act like that for a wormhole, counteracting the crushing force trying to snap it shut the moment it forms. The real kicker: this isn't just some wild guess. Quantum mechanics hints that negative energy might not be pure fantasy. Tiny amounts of it could exist in the form of what's called Casimir energy, a weird quantum effect where empty space itself can produce negative pressure between two closely placed metal plates. It's as if the universe is whispering, here's a tiny taste of what you'd need, but scaling that up to the levels required for a traversable wormhole. That's like trying to power a starship with an AA battery. The energy densities needed are mind-boggling, far beyond anything we've ever observed or engineered. And that's not even the biggest catch. Negative energy matter, if it exists, would defy everything we know about the behavior of particles. It would have to move toward you when pushed away, accelerate in the opposite direction of any force applied, like a cosmic version of Murphy's Law where physics works backward. Some theories suggest it might lurk in the quantum foam of spacetime or be manufactured through advanced manipulation of quantum fields, but for now it remains firmly in the realm of theory. So while negative energy offers a tantalizing solution to the wormhole stability problem, it's also a glaring reminder of how much we still don't understand. It's one thing for the math to allow something. It's another to find or create the physical stuff that makes it real. Until then, the dream of stepping through a cosmic shortcut remains locked behind a door we're still learning how to pick. But if we ever crack it, the universe might suddenly become a lot smaller. Now, let's zoom in way in down to the very fabric of reality itself. At the smallest scales imaginable, space-time isn't smooth and serene like a calm ocean. It's more like a bubbling, frothing stew, constantly churning with tiny fluctuations. This is the quantum foam, a chaotic sea of virtual particles popping in and out of existence, twisting space-time into microscopic knots. And buried in that chaos, some physicists believe, could be the seeds of wormholes, tiny, ephemeral tunnels flickering into being and vanishing almost instantly. The quantum foam hypothesis comes from an eerie prediction of quantum mechanics. That empty space isn't truly empty. At scales a billion times smaller than an atom, so-called virtual particles borrow energy from the vacuum, briefly forming pairs before annihilating each other. This ceaseless activity warps spacetime into a turbulent foam, where infinitesimal wormholes might spontaneously form and collapse. Picture a pot of boiling water, with bubbles constantly rising and bursting, except here, the bubbles are spacetime itself, and some might briefly tunnel to another point in the universe. But here's the catch: these quantum wormholes would be unimaginably small, lasting for fractions of a second before disappearing. To make them useful for travel, we'd need to somehow stabilize and stretch them to macroscopic sizes, like trying to enlarge a soap bubble without popping it. The energy required would be staggering, far beyond anything our current technology can muster. Some theories suggest manipulating the fabric of spacetime with ultra-dense materials or harnessing the energy of entire stars. Others propose using quantum entanglement, the strange link between particles across vast distances, to somehow pin a wormhole open. But these ideas are purely speculative, pushing the limits of known physics. Even if we could scale them up, quantum wormholes would come with mind-bending paradoxes. Passing through one might scramble the very laws of cause and effect, creating loops where an event could happen before its own cause. Time itself could become tangled, leaving physicists grappling with questions that defy logic. And then there's the haunting possibility that these tunnels might not lead where or when we expect. A microscopic wormhole might connect 2 points a millimeter apart, or it could bridge entirely different universes in a vast cosmic multiverse. So while the quantum foam hypothesis offers a tantalizing glimpse into how wormholes might arise naturally, it also highlights the immense hurdles standing in our way. These tunnels might be woven into the universe's smallest seams, but unlocking their potential would require rewriting the rules of physics as we know them. For now, they remain ghostly whispers in the quantum static, hints of a deeper reality where space and time are far stranger than we ever imagined. Black holes have long been the universe's ultimate enigmas, cosmic traps where gravity wins so utterly that not even light can escape. But what if these terrifying voids aren't just dead ends? What if hidden deep within their crushing cores lies a secret passage? Some physicists speculate that the very thing we thought was a one-way ticket to oblivion might actually be the mouth of a wormhole, a gateway to somewhere or someone else entirely. At the heart of this idea is the singularity, the point inside a black hole where gravity becomes infinite and space-time curves beyond comprehension. According to Einstein's equations, matter falling into a black hole doesn't just vanish, it gets compressed into an infinitely dense, infinitely small point. But here's where things get weird. If you reverse the math, that same singularity could theoretically unfold into a white hole, a hypothetical region where matter and energy spew outward instead of being sucked in. Connect the two, and you've got a wormhole, a tunnel threading through the fabric of spacetime itself. The catch: this would defy the famous no-hair theorem, which suggests black holes are shockingly simple objects defined only by their mass, spin, and charge. If wormholes do lurk inside them, that simplicity shatters. Suddenly, black holes could hide intricate structures, cosmic backdoors with untold complexities. Imagine a library where every book looks identical on the outside, but open one, and you find an entire labyrinth tucked between its covers. That's the kind of paradox we're dealing with. But how could a wormhole survive the black hole's relentless gravity? One possibility is that the singularity isn't a point at all, but a ring singularity, as proposed in some rotating black hole models. Picture a donut-shaped vortex where centrifugal force counteracts gravity just enough to keep the tunnel open. Fall in the right way, and instead of being ripped apart, you might emerge in another universe, another time, or even another version of reality. Of course, the universe loves throwing curveballs. Even if black hole wormholes exist, their entrances would be shrouded by event horizons, those one-way boundaries where escape becomes impossible. That means if you did venture in, there'd be no coming back to tell the tale, at least not without violating every law of physics we know. And then there's the small matter of spaghettification, the process where tidal forces stretch you into a noodle long before you reach the center. Not exactly ideal travel conditions. Still, the idea lingers because it forces us to rethink the most extreme environments in the cosmos. If black holes aren't just cosmic trash compactors, if they're more like subway stations on a grand universal scale, then the universe just got a whole lot stranger. And who knows, maybe somewhere in the inky depths of a supermassive black hole, there's a door waiting to be opened. The only way to find out is to keep pushing the limits of what we think is possible. If a black hole is the universe's ultimate drain, sucking everything into its inescapable grip, then a white hole would be its opposite, a cosmic fire hose blasting matter and energy outward with unstoppable force. The idea is as elegant as it is unsettling. Wormholes might not just bridge 2 points in space, but could also have a hidden exit, a place where everything that falls in one side comes spewing out the other. Picture a tunnel with a black hole at one end and a white hole at the other, a one-way street through the fabric of reality. The math behind white holes emerges from the same equations that predict black holes, just flipped inside out. Where a black hole's event horizon traps everything forever, a white hole's would repel anything trying to enter, as if the universe itself were shouting, "No admittance." Instead of collapsing inward, spacetime would erupt outward, hurling matter and light into the cosmos like a geyser. For decades, white holes were dismissed as mathematical oddities, too bizarre to exist in nature. But if wormholes are real, they might need these explosive exits to balance the cosmic ledger. Here's where things get even weirder. Some theories suggest white holes could be the birth cries of entire universes. Imagine our Big Bang as the violent eruption of a white hole in some other, older cosmos, a place where another universe's black hole spat out everything that fell into it, birthing our own reality in the process. It's a dizzying thought. Every galaxy, star, and planet might just be the fallout from a wormhole's backdoor. But there's a glaring problem. White holes violate the second law of thermodynamics, the rule that says entropy, the universe's tendency toward disorder, always increases. A white hole would essentially be a cosmic reset button, ejecting matter in pristine, low-entropy states, like a scrambled egg reassembling itself in midair. That's why many physicists argue white holes can't exist, at least not in our universe's current era. The math might allow them, but nature seems to have other plans. Then again, nature has surprised us before. Some researchers speculate that white holes could be hiding in plain sight, masquerading as gamma-ray bursts, those blindingly energetic explosions that flicker across the cosmos. Others wonder if dark matter, the invisible glue holding galaxies together, could be the faint afterglow of ancient white holes, their remnants scattered like cosmic breadcrumbs. The truth is, we're still grappling with the basics. If white holes exist, they'd rewrite not just astrophysics, but our understanding of time itself. After all, a wormhole linking a black hole to a white hole isn't just a tunnel through space, it's a bridge between cause and effect, a place where the future might reach back to touch the past. And that's the real mystery, whether these cosmic fire exits are out there, waiting to be found, or just beautiful mirages in the desert of theoretical physics. For now, they remain one of the universe's most tantalizing what-ifs. Deep in the aftermath of the Big Bang, when the universe was just a seething cauldron of raw energy, physicists believe something extraordinary may have formed: cosmic strings. These bizarre, thread-like defects in spacetime aren't made of matter or energy, but of pure geometry, like cracks frozen in the fabric of reality itself. And if they exist, their mind-bending gravitational pull could twist spacetime into something even more incredible: natural wormholes. Cosmic strings are thought to be relics from a trillionth of a second after the universe began, when the fundamental forces of nature were still splitting apart. As the cosmos cooled, spacetime might not have smoothed out evenly. Instead, it could have formed ultra-dense, infinitely thin filaments, thinner than an atom but stretching across billions of light years. Imagine the universe as a block of ice freezing too fast, with hairline fractures trapped inside. Now imagine those fractures weigh more than entire galaxies. That's the sheer scale we're talking about. Here's where it gets wild. The gravity around a cosmic string wouldn't work like normal gravity. Because these strings are so unimaginably dense, they'd warp spacetime into a sharp, cone-like shape around them. If two strings crossed or looped close together, their combined gravitational fields could pinch spacetime so violently that it forms a tunnel, a wormhole bridging two distant points. Picture holding two strands of spaghetti under tension until they snap together, creating a fleeting bridge between them. That's the kind of gravitational gymnastics we're dealing with. But could these tunnels actually be traversable? The math suggests it's possible, though with some universe-sized asterisks. Unlike black hole wormholes, which crush anything that enters, a cosmic string wormhole might lack an event horizon, meaning you could theoretically pass through without being shredded. The catch: you'd need to move at nearly the speed of light to avoid the string's gravitational pull snapping the tunnel shut behind you. Even a slight miscalculation, and you'd be stretched into a particle stream across millennia. The real challenge is finding these elusive strings. they'd be invisible to telescopes, detectable only by their gravitational fingerprints, subtle distortions in the light of distant galaxies, or sudden bursts of gravitational waves as they vibrate like plucked guitar strings. Some researchers have scoured the cosmos for these telltale signs, but so far, no smoking gun. Still, the hunt continues, because if cosmic strings are out there, they might not just be relics of the past, they could be the universe's original subway system, hidden in plain sight. And then there's the tantalizing possibility that these strings aren't just ancient artifacts. Some theories suggest they could still be forming in the hearts of galaxies or colliding neutron stars, creating fresh wormholes in the modern universe. It's a reminder that the cosmos might be far more dynamic and far more connected than we ever dared to dream. So while cosmic strings remain theoretical, they offer something priceless, a glimpse into how space-time itself might be threaded with shortcuts, waiting for us to pull the right string. Dark matter has always been the universe's quiet enforcer, an invisible hand shaping galaxies, bending light, and holding the cosmos together without ever revealing itself. But what if its hidden influence goes deeper? What if this mysterious substance isn't just holding stars in place, but secretly weaving tunnels through space-time itself? Some scientists suspect dark matter could be the missing ingredient that makes wormholes not just possible, but stable enough to traverse. Here's why this idea isn't as far-fetched as it sounds. Dark matter makes up roughly 85% of the universe's mass, yet it doesn't interact with light or ordinary matter in any way we can directly detect. Its presence is only betrayed by its gravity. The way it tugs on galaxies, warps distant starlight, and keeps entire clusters from flying apart. That gravitational dominance is key. If dark matter isn't just scattered randomly, but clustered in specific, dense configurations, its pull could theoretically warp space-time into a tunnel-like structure. Picture draping a weighted blanket over a trampoline. The heavier the weights, the deeper the dips, until the fabric pinches together. Dark matter could be doing the same to space-time, creating natural wormholes at cosmic crossroads where its gravity is strongest. But there's a twist. Ordinary matter alone can't stabilize a wormhole. It would collapse instantly under its own gravity. That's where dark matter's other eerie property comes in, its ability to clump without collapsing. Unlike stars or gas, dark matter doesn't radiate energy or slow down, meaning it can form dense, stable structures without overheating or dispersing. Some models suggest these structures could act like gravitational scaffolding, holding a wormhole open just long enough for something to slip through. Think of it as cosmic rebar, reinforcing the tunnel against the crushing weight of space-time trying to snap it shut. The real puzzle is whether dark matter could make these tunnels traversable. One provocative theory involves a hypothetical form of dark matter called mirror matter, particles that interact only with each other through their own invisible forces. If these particles clustered in just the right way, they might create a repulsive effect inside a wormhole, counteracting gravity's inward pull like an anti-collapse mechanism. It's the same principle as negative energy, but with a dark matter twist. Of course, we're still grasping in the dark, literally. Without knowing what dark matter is, we can't say for sure if it has the right properties to engineer space-time shortcuts. But the tantalizing clues keep stacking up. Some wormhole models align suspiciously well with observed dark matter distributions in galaxies, as if the universe is quietly hinting at a connection. And if dark matter turns out to be something even stranger, like primordial black holes or particles from extra dimensions, all bets are off. The irony is delicious. The very stuff we've spent decades trying to detect might be the key to unlocking the universe's greatest shortcuts. If dark matter can stabilize wormholes, then every galaxy could be threaded with hidden passages, waiting for us to decode their secrets. Until then, we're left with a haunting possibility that the answer to interstellar travel has been floating right beside us all along, invisible, silent, and just out of reach. Time travel isn't just a trope from science fiction, it's a genuine possibility if wormholes exist. The equations of general relativity don't just allow for shortcuts through space. They suggest these tunnels could also bridge different moments in time, turning a journey across the cosmos into a leap through history. But here's the catch. Opening that door doesn't just defy physics, it unravels logic itself, creating paradoxes so baffling they've kept philosophers and scientists awake for decades. Take the grandfather paradox, the ultimate thought experiment in temporal chaos. Imagine you step through a wormhole and travel back to a time before your grandfather had children. If you were to intentionally or accidentally prevent his meeting with your grandmother, you'd erase your own existence. But if you never existed, who went back in time to interfere in the first place? It's a loop of cause and effect that collapses like a house of cards. The universe, it seems, has a strict no-refunds policy when it comes to causality. The paradox doesn't stop there. What if you used a wormhole to send information, or even yourself, back just a few minutes to prevent a disaster? Success would mean the disaster never happened, so there'd be no reason to go back, meaning the disaster would happen, and round the loop goes. These contradictions aren't just brain teasers, they strike at the heart of how we understand reality. Time, as we experience it, is a one-way street. Wormholes could turn it into a Möbius strip where past and future tangle in ways that defy resolution. Physicists have proposed wild solutions to these puzzles, like the idea of parallel timelines. In this scenario, traveling back through a wormhole wouldn't change your past but would instead spin off a new, alternate universe where events play out differently. It's like hitting a fork in the road, except the road splits into infinite branches, each a self-contained reality where every possible outcome exists simultaneously. Suddenly, the grandfather paradox isn't a paradox at all, just a detour into another version of events where you were never born, while your original timeline remains untouched. But even this escape hatch has its critics. Quantum mechanics suggests that parallel universes might exist, but stitching them together with wormholes raises new questions. Would these tunnels connect to any timeline or just specific ones? Could you hop between them at will, or would the universe enforce some kind of chronological traffic control? And if time travel is possible, why haven't we met visitors from the future? Some argue that wormholes might only allow travel back to the moment they were created, like a bridge you can't cross until it's built, locking the past away like a forbidden room. Then there's the less discussed but equally mind-bending predestination paradox, where your actions in the past were always part of history. Picture using a wormhole to go back and give younger you the secret to time travel. Where did that knowledge originate? It's a closed loop with no starting point, like a snake swallowing its own tail. The universe might simply tolerate these paradoxes, weaving them seamlessly into the fabric of events without breaking a sweat. After all, if time is just another dimension, maybe causality is more flexible than we think. The truth is, we're playing with concepts at the very edge of comprehension. Wormholes challenge not just our understanding of physics, but the nature of existence itself. They force us to ask whether time is a river flowing in one direction or an ocean with currents too complex to map. And until we find or build a real traversable wormhole, these paradoxes will remain thought experiments, taunting us with possibilities just beyond our grasp. But one thing's certain, if we ever do crack the code of time travel, the universe's rulebook might need a serious rewrite. Some of the most radical ideas in physics suggest our entire universe might be a hologram, a three-dimensional projection of information encoded on a distant, two-dimensional surface. It sounds like something straight out of the Matrix, but the holographic principle is a serious scientific proposal, born from attempts to reconcile quantum mechanics with black hole physics. And if it's true, wormholes might not just be tunnels through space, they could be glitches in the cosmic projection, revealing glimpses of a higher dimensional reality we can't normally perceive. The holographic principle emerged from a startling discovery about black holes. When matter falls into one, it doesn't just vanish, the information it carries gets imprinted on the black hole's event horizon, the boundary where light can no longer escape. This means the entire three-dimensional reality of the infalling matter is somehow encoded on a two-dimensional surface, like a movie being stored on a DVD. Physicists like Leonard Susskind and Gerard T. Hooft theorized that if this works for black holes, maybe the entire universe operates the same way. In this view, everything we experience, stars, galaxies, even our own thoughts, might just be shadows cast by processes happening on an unimaginably distant boundary at the edge of spacetime. So where do wormholes fit in? If our universe is a hologram, then wormholes could be shortcuts not just through space, but through the very fabric of the projection itself. Think of it like a video game where two distant points on the map are actually right next to each other in the underlying code. A wormhole might be a bug or feature that lets you exploit that hidden closeness. Some versions of the holographic principle even suggest wormholes could be projections of higher dimensional structures, like how a shadow of a twisted rope might look like two separate circles on a wall. In reality, they're connected in ways the flat surface can't show. The implications are dizzying. If wormholes are holographic artifacts, then their behavior might follow rules we can't perceive from within our limited 3D perspective. They could flicker in and out of existence as the underlying code updates, or change destinations based on higher dimensional geometry we can't measure. It's like trying to understand Wi-Fi signals by only studying the blinking lights on your router. There's a whole invisible layer dictating how everything works. But here's the real mind bender. If the holographic principle is correct, then traversing a wormhole might not mean moving through space at all. Instead, you'd be rewriting the information that defines your location in the cosmic projection, like editing your coordinates in a simulation. That could explain why wormholes seem to defy conventional physics. They're not bending spacetime so much as accessing the deeper rules that generate it. Of course, this is all speculative. The holographic principle remains unproven, and even its advocates admit we're centuries away from testing it directly. But if there's even a sliver of truth to this idea, then wormholes aren't just cosmic shortcuts, they're cracks in the illusion, offering a peek behind the universe's curtain. And that raises an unsettling question. If we ever do step through one, what or who might be waiting on the other side? String theory takes the idea of wormholes and twists it into something even stranger, because in this framework, the universe isn't just the three dimensions we know and love. It's a sprawling cosmic landscape with at least 6 extra dimensions, curled up so tightly we've never noticed them. And hidden in that intricate geometry, some physicists believe, could be the ultimate shortcut, wormholes woven from the very fabric of higher dimensional space. At the heart of string theory are Calabi-Yau manifolds, exotic, 6-dimensional shapes that exist at every point in our familiar 3-dimensional space, like tiny, hidden origami folds. These shapes aren't just mathematical curiosities. They determine how strings, the fundamental vibrating threads of reality, move and interact, shaping everything from particle physics to gravity. Now here's where it gets wild. If these Calabi-Yau manifolds twist in just the right way, they could pinch spacetime into a tunnel connecting 2 distant points. Picture a sheet of paper crumpled into a ball. From our limited 3D perspective, 2 points might seem far apart, but in higher dimensions they could be touching. That's the kind of hidden proximity string theory suggests might exist all around us. But the real game changer comes with brain world scenarios. In these models, our entire universe could be a 3-dimensional brain floating in a higher dimensional space called the bulk. Other brains might hover nearby, separated by dimensions we can't perceive. Normally, we're stuck on our brain like ants crawling on the surface of a leaf, oblivious to the rest of the tree. But wormholes could change that. Hypothetically, a wormhole in this framework could bridge 2 brains or 2 points on our own brain by threading through the bulk. It's like drilling a hole through the leaf instead of crawling all the way around the edge. The catch, these higher dimensional wormholes would demand mind-bending precision. To stabilize them, you'd need to manipulate the extra dimensions somehow, perhaps by vibrating strings in just the right pattern or harnessing energy from colliding branes. Some models even suggest that cosmic strings, those ultra-dense space-time defects, could act as anchors, pinning wormholes open like tent poles in the fabric of reality. And then there's the haunting implication. If wormholes can connect branes, they might not just be shortcuts through space. They could be gateways to entirely other universes with different physical laws. Imagine stepping through a tunnel and emerging in a reality where gravity is twice as strong, or where time flows backward. It's a dizzying thought, but in string theory's kaleidoscopic landscape, it's not off the table. Of course, all of this hinges on whether string theory itself holds water. After decades of research, we still lack direct evidence for extra dimensions or vibrating strings. But if they're out there, woven into the universe's deepest layers, then wormholes might not be anomalies at all. They could be inevitable features of a cosmos far richer and far weirder than we've ever imagined. The Big Bang wasn't just the beginning of our universe, it was a moment of such unimaginable energy and chaos that the very laws of physics might have bent to their breaking point. In those first searing fractions of a second, space-time itself could have twisted into shapes we'd struggle to recognize today. And buried in that primordial turbulence, some physicists believe, might lie the universe's first wormholes, not as rare anomalies, but as cosmic fossils from the birth of everything. Think of it like cooling glass. When molten glass hardens, tiny imperfections get frozen into its structure, air bubbles, warps, and subtle ripples that tell the story of how it formed. If space-time behaved similarly during the initial expansion of the universe, wormholes could be those imperfections. The extreme temperatures and densities of the early cosmos would have created ideal conditions for space-time to fold, knot, or even tear, leaving behind tunnels threading through the newborn universe. Unlike wormholes that might form later from black holes or quantum foam, these primordial passages would have been baked into reality from the very beginning like cracks in a rapidly expanding cosmic souffle. But could they still exist today? That's where things get tricky. The universe has stretched by a factor of 1 trillion since those first moments, smoothing out most wrinkles in space-time. Any wormholes formed back then would have either been stretched to cosmological scales or pinched off into oblivion unless something kept them stable. One tantalizing possibility involves hypothetical particles called actions, which some theories suggest were abundant in the early universe. These ultra-light particles might have acted like cosmic glue, reinforcing wormholes against the violent expansion, preserving them like insects trapped in amber. Then there's the question of where they'd be hiding. If Big Bang wormholes survived, they wouldn't necessarily look like the sleek tunnels of sci-fi. They might be gargantuan, spanning entire galaxy clusters, or so microscopic they'd flicker in and out of existence at the Planck scale. Some models even suggest they could be disguised as dark matter halos, those invisible cocoons surrounding galaxies. After all, if wormholes are warps in spacetime and dark matter's gravity also warps spacetime, could the two be intertwined? It's a provocative thought. The missing mass we've been hunting for decades might actually be a network of ancient wormholes woven into the fabric of the cosmos. Yet the biggest hurdle is time itself. Over billions of years, even stable wormholes would face relentless erosion from quantum fluctuations, gravitational waves, and the expansion of the universe. Like sandcastles on a beach, they might have slowly dissolved, leaving behind only faint echoes, perhaps imprinted in the cosmic microwave background, the afterglow of the Big Bang. Or maybe, just maybe, a few survived intact, lurking in the voids between galaxies, waiting for us to stumble upon them. The hunt is already underway. Astronomers scour the sky for anomalies, unexplained gravitational lensing, bizarre temperature variations in the cosmic microwave background, or stars that seem to vanish and reappear without cause. Each could be a clue, a fingerprint of those primordial tunnels, and if we ever find one, it wouldn't just rewrite the story of wormholes, it would give us a front-row seat to the universe's very first moments, a glimpse into the furnace where everything began. So while the idea of Big Bang wormholes remains speculative, it's a reminder that the universe's earliest seconds were anything but ordinary. In that cauldron of creation, the rules were still being written, and some of those rules might have left doors open, just wide enough for us to dream of stepping through. Imagine holding the ultimate cosmic construction manual, one with step-by-step instructions for building your own wormhole. While nature might have formed the first ones in the chaos of the Big Bang, human ingenuity could theoretically engineer one from scratch if we master physics far beyond our current grasp. The blueprints already exist in the equations of general relativity, hinting at two radical approaches: bending space-time with unfathomable energy, or stitching together quantum-scale tunnels until they're large enough to traverse. Either way, the challenges are as staggering as the rewards. Start with the Alcubierre drive, often dubbed the warp drive in sci-fi circles. Proposed by physicist Miguel Alcubierre in 1994, this concept doesn't create a wormhole in the traditional sense, it manipulates space-time itself. Picture a bubble forming around a spacecraft with space-time compressed in front of it and expanded behind. The ship wouldn't move through space, space would move around the ship, effectively allowing faster-than-light travel without breaking Einstein's speed limit. The catch: generating this warp bubble requires negative energy exotic matter with repulsive gravity, the same elusive ingredient needed for stable wormholes. Current estimates suggest you'd need the energy equivalent of Jupiter's mass converted into negative energy just to warp space-time enough for a small ship. That's like trying to power a city with a single-A battery, but there's another path, exploiting the quantum weirdness of the Casimir effect. In a vacuum, virtual particles flicker in and out of existence, creating tiny fluctuations in energy. Place two metal plates extremely close together, and these fluctuations produce a measurable force, an attractive pull between the plates. More intriguingly, the space between them develops negative energy density, a microscopic hint of the exotic matter wormholes demand. Scale this effect up, and you might theoretically line a wormhole's throat with Casimir energy to keep it propped open. The problem: the plates would need to be impossibly close, think subatomic distances, and the energy harvested would be vanishingly small. We're talking about needing more Casimir plates than atoms in the observable universe just to stabilize a tunnel big enough for a proton. And then there's the engineering nightmare of construction itself. Even if we solved the energy problem, building a wormhole isn't like digging a subway tunnel. Space-time isn't passive, it fights back. The moment you create a wormhole, gravitational forces would try to collapse it, requiring constant reinforcement. Some theories suggest using cosmic strings, those ultra-dense space-time defects, as scaffolding to prevent collapse. Others propose manipulating dark energy, the mysterious force accelerating the universe's expansion, to counteract gravity's pull. Both ideas sound like something from a far future textbook, requiring technologies that might as well be magic by today's standards. But perhaps the biggest hurdle isn't physics, it's control. A man-made wormhole wouldn't just be a tunnel, it'd be a terrifyingly powerful gravitational anomaly. Miscalculated stability, and it could collapse into a black hole, vaporizing everything nearby. Even a stable wormhole would radiate intense Hawking radiation at its entrance, frying any approaching spacecraft. And if time dilation effects kick in, something almost guaranteed with such extreme spacetime curvature, you might step through only to find centuries have passed on Earth. Yet for all these obstacles, the pursuit isn't futile. Breakthroughs in quantum physics, metamaterials, and energy manipulation are inching us closer to concepts once deemed pure fantasy. The Alcubierre drive has inspired NASA-funded research, while Casimir effect experiments grow more sophisticated yearly. What seems impossible today might just be tomorrow's engineering manual. After all, the Wright brothers once dreamed of flight, and look where we are now. The universe may not give up its shortcuts easily, but that doesn't mean we'll stop trying to build them ourselves. Quantum entanglement and wormholes might seem like entirely separate puzzles, one belonging to the bizarre world of subatomic particles, the other to the vast reaches of spacetime. But what if they're two sides of the same cosmic coin? That's the radical idea behind ER equals EPR, a theory that stitches together Einstein's work on wormholes with his skepticism toward quantum entanglement. It suggests that every entangled pair of particles could be connected by a microscopic wormhole, a hidden bridge threading through the fabric of reality itself. The theory's name is a mashup of two landmark ideas. Refers to the Einstein-Rosen Bridge, the first mathematical description of a wormhole, while EPR stands for Einstein-Podolsky-Rosen, a famous thought experiment highlighting the spooky nature of quantum entanglement. At first glance, these concepts couldn't be more different. Entanglement links particles instantaneously across any distance, so that measuring one automatically determines the state of the other, something Einstein called spooky action at a distance. Wormholes, meanwhile, are tunnels through space-time, bending the rules of locality by offering a shortcut between distant points. But in 2013, physicists Juan Maldacena and Leonard Susskind proposed a jaw-dropping connection. What if entanglement is a wormhole in disguise? Think of it like a secret passage between two rooms. From the outside, the rooms appear separate, but open a hidden door and they're intimately linked. In the ER equals EPR framework, entangled particles aren't just correlated, they're literally connected by a Planck-scale wormhole, a tunnel so tiny it's buried deep in the quantum foam. This would mean entanglement isn't some ethereal link but a geometric feature of spacetime itself, etched into its very structure. The implications are staggering. If true, this theory could unify quantum mechanics and general relativity, the holy grail of modern physics. Quantum mechanics governs the tiny, probabilistic world of particles, while general relativity describes the smooth, deterministic curvature of spacetime. They've resisted reconciliation for over a century, but if entanglement arises from microscopic wormholes, it would mean quantum weirdness is rooted in spacetime geometry. Suddenly, the probabilistic nature of particles might emerge from the chaotic twists and folds of these hidden tunnels. Yet there's a catch. These wormholes would be non-traversable, far too small and unstable for anything to pass through. They'd be more like cosmic stitching, holding the fabric of reality together at the seams. But some theorists speculate that with enough entangled particles, you might somehow weave a macroscopic wormhole into existence. Picture billions of entangled pairs, their microscopic bridges merging into a tunnel large enough to traverse. It's like building a rope from individual threads, each one insignificant alone but together impossibly strong. The irony is delicious. Einstein spent years railing against entanglement's spookiness, insisting physics should be local and deterministic. Now, his own equations suggest that spookiness might be the key to spacetime's deepest secret. And while ER equals EPR remains speculative, experiments with quantum computers and holographic simulations are beginning to test its predictions. Who knows? The universe's first wormholes might not lie in distant galaxies. They could be flickering in every entangled particle around us, whispering that the fabric of reality is far stranger than we ever dreamed. What if every wormhole is more than just a shortcut across our universe? What if it's a doorway to another reality entirely? The idea that these cosmic tunnels could bridge parallel dimensions isn't just sci-fi speculation. It's a serious theoretical possibility, one that reshapes how we think about the very nature of existence. According to the many worlds interpretation of quantum mechanics, every decision, every random event, spins off a new universe where history unfolds slightly differently. And if that's true, wormholes might be the thread stitching this infinite tapestry of realities together. Picture this: you step through a wormhole expecting to emerge in a distant galaxy, but instead you find yourself in a world where the laws of physics are subtly or drastically different. Maybe gravity is weaker here, or light travels at half its usual speed. Perhaps humanity never evolved, or dinosaurs still rule the planet. In the multiverse framework, every possible outcome exists somewhere, and wormholes could be the cosmic elevators shuttling between these infinite floors. The mathematics of general relativity doesn't forbid it. Certain solutions even suggest wormholes could naturally terminate in other universes, like roots tunneling through soil into neighboring gardens. But how would these cross-dimensional wormholes form? One chilling possibility ties back to black holes. When matter collapses into a singularity, some models suggest it doesn't just vanish, it might puncture space-time like a needle through fabric, birthing a new universe on the other side. Our Big Bang could have been the white hole eruption of a black hole in another cosmos, meaning every black hole in our universe might secretly be a creator, not a destroyer. Wormholes formed in these cataclysms could linger as umbilical cords between parent and offspring universes, hidden in the aftermath of creation. The implications are dizzying. If wormholes can bridge parallel worlds, they wouldn't just defy space, they'd shatter the concept of a single, linear timeline. You might return from a journey to find your home universe unrecognizable, or meet alternate versions of yourself who took different paths. The many worlds interpretation sidesteps classic time travel paradoxes. There's no grandfather paradox if you're just hopping to a branch where your grandfather never met your grandmother. But it introduces new nightmares like quantum contagion. What happens if a physical law or destabilizing force leaks through the wormhole, unraveling the fabric of one or both universes? Then there's the haunting question of detection. If multiverse wormholes exist, how would we know? Some theorists propose looking for gravitational anomalies, places where space-time curvature defies explanation, as if tugged by mass in an adjacent reality. Others suggest hunting for impossible particles or energy signatures leaking through, like echoes from a room we can't see. The cosmic microwave background, the afterglow of the Big Bang, might even bear scars from ancient collisions with other universes, faint bruises hinting at a larger cosmic neighborhood. But the most profound implication isn't scientific, it's philosophical. If wormholes open doors to other worlds, then our choices suddenly carry infinite weight. Every road not taken, every chance event plays out somewhere in the multiverse. A wormhole could be the universe's way of reminding us that we're not just actors on a stage, but explorers in a labyrinth of limitless possibilities. And somewhere out there, in a reality almost like ours, another version of you might be standing at the mouth of the same tunnel, wondering what lies on your side. Dark energy is the universe's silent architect, an invisible force pushing galaxies apart at an ever-increasing pace. It's the reason our cosmos isn't just expanding, it's accelerating, stretching space-time itself like dough in an infinite oven. But here's the cosmic irony. While dark energy rips the universe apart on grand scales, it might hold the key to keeping wormholes, those hypothetical space-time tunnels, from collapsing in on themselves. The relationship between these two phenomena isn't just a curiosity. It's a battle between two fundamental forces of nature, and the outcome could decide whether traversable wormholes are even possible. On one hand, dark energy's repulsive gravity is the exact opposite of what keeps traditional wormholes unstable. Remember, wormholes need some form of negative energy or exotic matter to counteract the crushing force of their own gravity, propping them open like a tunnel reinforced with cosmic steel beams. Dark energy, with its bizarre ability to push space-time outward instead of pulling it inward, seems like the perfect candidate for the job. Picture a wormhole's throat as a narrow hallway. Dark energy could act like someone leaning against the walls, preventing them from slamming shut. In theory, if you could somehow concentrate dark energy around a wormhole, it might stabilize the tunnel long enough for something to pass through, but the universe rarely makes things that simple. Dark energy's expansion isn't localized, it's a background effect permeating all of space, and its strength grows as the universe empties out over time. That means it doesn't just push, it stretches, diluting the very fabric of spacetime on cosmic scales. For a wormhole, this could be catastrophic. Imagine trying to keep a rubber band taut while someone slowly pulls it apart from both ends. Even if dark energy counters the wormhole's inward collapse, the relentless expansion of space might thin the tunnel's walls until they rupture, like a soap bubble popping in midair. Some models suggest that over billions of years, dark energy could stretch wormholes so thin they'd effectively evaporate, leaving behind only faint gravitational echoes. Then there's the wild card, phantom energy, a hypothetical form of dark energy that doesn't just accelerate the universe's expansion, but does so at an ever-increasing rate. In this scenario, the universe's fate is the Big Rip, where galaxies, stars, and even atoms are torn apart in a final, violent crescendo. If phantom energy exists, its influence on wormholes would be downright apocalyptic. Instead of gently stretching them, it could shred spacetime at the quantum level, snapping wormholes like overstretched guitar strings long before the universe's final moments. Yet not all hope is lost. Some cutting-edge theories propose that dark energy's expansion and wormhole stability might find an uneasy balance. If dark energy isn't perfectly uniform, if it clumps or fluctuates in certain regions, those pockets could theoretically create temporary, sweet spots where wormholes thrive. Think of it like surfing a wave. The ocean is vast and powerful, but a skilled surfer can ride just the right curve to stay aloft. Similarly, a wormhole nestled in a region where dark energies push and spacetime's tension cancel each other out might persist far longer than its surroundings. The real twist, dark energy itself might be entangled with the existence of wormholes. Some models suggest that the same quantum fields responsible for dark energy could, under extreme conditions, generate tiny wormholes as byproducts. It's as if the universe's expansion and its hidden shortcuts are two sides of the same coin, locked in an eternal dance. If true, then searching for wormholes might not just be about finding cosmic shortcuts, it could help us unravel the deepest mystery in modern cosmology, what dark energy actually is. So while dark energy poses a formidable challenge to wormhole stability, it's also a reminder that the universe loves paradoxes. The very force driving galaxies apart might one day be the tool we use to stitch the cosmos together. And if we ever learn to harness it, the ultimate cosmic commute could be closer than we think. In the first chaotic moments after the Big Bang, when the universe was hotter than a trillion suns and smaller than a single atom, reality itself was in a state of quantum frenzy. Space and time hadn't yet settled into the smooth, predictable fabric we know today. They were a boiling sea of fluctuations, bubbling with violent energy shifts that could have twisted spacetime into knots. And in that primordial chaos, something extraordinary might have happened. Wormholes could have formed spontaneously, like microscopic whirlpools in the cosmic storm. These weren't the carefully constructed tunnels of sci-fi dreams. They were quantum accidents, fleeting fractures in the newborn universe that could have survived, hidden to this very day. The conditions were perfect for such anomalies. In that first unimaginable second, the universe expanded faster than the speed of light during a period called inflation, stretching spacetime like taffy. Quantum fluctuations, tiny, random variations in energy, were magnified to cosmic scales, imprinting wrinkles that eventually grew into galaxies and galaxy clusters. But some of those fluctuations might have been so extreme that they pinched spacetime into loops, creating microscopic wormholes woven into the fabric of the cosmos. Picture blowing up a balloon with tiny weak spots as it inflates. Some of those spots might stretch into tunnels rather than tears. But here's the trillion-dollar question. Could any of these wormholes have survived 14 billion years of cosmic evolution? The universe is a brutal place for delicate structures. Expansion would have pulled most primordial wormholes apart, stretching them until they snapped like overextended rubber bands. Radiation from the Big Bang's afterglow could have bombarded them with enough energy to destabilize their fragile throats. Even the relentless tug of dark energy pushing galaxies apart might have slowly unraveled them over eons. Yet some theorists argue that a lucky few could have endured if they were reinforced by something exotic. One possibility involves cosmic strings, those ultra-dense filaments of space-time leftover from the early universe. If a wormhole formed around or within one of these strings, its immense gravitational pull might have acted like a support beam, preventing the tunnel from collapsing. Another hypothesis suggests that dark matter, the invisible scaffolding of the cosmos, could have clustered around these wormholes, its gravity counteracting the forces trying to erase them. It's like imagining a spiderweb surviving a hurricane because it's anchored to something unshakable, except here, the web is space-time itself, and the anchor is a mystery we're still trying to solve. Then there's the eerie chance that some primordial wormholes didn't just survive, they grew. As the universe expanded, regions with stronger gravitational pulls like galaxy clusters may have stretched nearby wormholes along with them, enlarging microscopic passages into cosmic-scale shortcuts. A wormhole that started smaller than a proton could now span light years, hidden in the voids between galaxies where gravity's grip is weakest. Astronomers have even speculated that certain gravitational lensing anomalies, places where distant starlight bends in ways that defy explanation, could be the fingerprints of these ancient tunnels warping spacetime around them. But if they're out there, how would we find them? The hunt would require looking for the universe's subtlest clues. Primordial wormholes wouldn't emit light or radiation. They'd be nearly invisible. Instead, scientists scan for distortions in the cosmic microwave background, the faint echo of the Big Bang, where a wormhole's gravitational shadow might leave a telltale swirl. Others propose watching for stars that flicker unpredictably as their light passes near a hidden wormhole's entrance, or tracking rogue gravitational waves that don't match any known black hole collision. The most tantalizing idea of all, some of these relics might still be active. While most primordial wormholes would have collapsed or drifted apart, a rare few could remain stable enough to function, not as tunnels for spacecraft but as windows. If we could peer into one, we might glimpse the universe in its infancy, a freeze frame of creation itself. That's the real magic of this theory. It suggests that the cosmos might still hold its first blueprints, etched into space-time and waiting to be read. The catch, of course, is that we're still learning how to look, but if we ever find one, it won't just rewrite the history of wormholes, it'll rewrite the history of everything. When two neutron stars spiral toward each other in a final, violent embrace, the collision is so powerful it shakes the very fabric of space-time. These ultra-dense stellar corpses, each packing a sun's worth of mass into a city-sized sphere, warp reality so intensely that their merger could briefly tear open a wormhole, offering a fleeting shortcut through the cosmos. It's a staggering idea that the universe's most cataclysmic events might not just destroy matter but twist it into doorways. The physics behind this begins with the neutron stars themselves. Born from the collapsed cores of exploded supergiant stars, they're so dense that a single teaspoon of their material would weigh billions of tons on Earth. Their surfaces are smooth as perfect mirrors, their gravity so strong it bends light into bizarre halos. When two of these objects orbit each other, they emit gravitational waves, ripples in spacetime predicted by Einstein, slowly losing energy until they collide in a kilonova explosion brighter than a million suns. But in the milliseconds before impact, their combined gravitational fields might stretch spacetime to the breaking point. During the merger, simulations suggest the star's cores could momentarily form a hypermassive neutron star, a single, unstable object teetering on the edge of becoming a black hole. In that critical window, the extreme curvature of spacetime might pinch into a wormhole throat. Picture two whirlpools merging in a bathtub. For an instant, their vortices could connect underwater, creating a tunnel between them. Similarly, the neutron stars' combined gravity could twist spacetime into a transient bridge, linking their former locations across light years. The catch: this wormhole wouldn't last. Within fractions of a second, the hypermassive neutron star would either collapse into a black hole or explode, severing the tunnel like a rope under tension. Anything attempting passage would be shredded by tidal forces or vaporized in the kilonova's fury. Yet even this ephemeral existence raises tantalizing possibilities. Some theories propose that quantum particles, which can tunnel through barriers via probabilistic quirks, might traverse these brief wormholes unscathed. If so, the mergers could be cosmic portals for information, if not matter, sending data encoded in particles from one point to another instantaneously. What's even wilder is how we might detect such an event. Gravitational wave observatories like LIGO and Virgo have already captured neutron star mergers, but a wormhole's signature would be distinct. Instead of the characteristic chirp of colliding objects, scientists might detect an echo, a faint gravitational rebound as spacetime snaps back into place post-collapse. Or they could spot anomalies in the afterglow, like missing energy or bizarre particle trajectories hinting at a hidden tunnel siphoning material away. The implications reach beyond astrophysics. If neutron star mergers can birth wormholes even briefly, it suggests spacetime is far more malleable than we thought, that under the right conditions, the universe might spontaneously knit itself into shortcuts. It's a humbling reminder that the cosmos doesn't just contain mysteries, it is the mystery constantly rewriting its own rules in the crucible of extreme events. And somewhere out there, in the darkness between stars, two dead suns might be clashing in ways we're only beginning to imagine. What if the key to traversing a wormhole isn't just advanced technology, but advanced consciousness itself? The idea that the human mind, or perhaps an artificial intelligence beyond our current capabilities, could be the missing ingredient for stabilizing these cosmic tunnels sounds like something straight out of science fiction. Yet some physicists and philosophers argue that the very nature of wormholes, their instability, their defiance of classical physics, their potential entanglement with quantum reality, might demand a navigator that operates outside the bounds of ordinary perception. Think about it like this: wormholes aren't just physical structures, they're dynamic distortions in space-time where the rules of cause and effect bend and the fabric of reality becomes fluid. Trying to traverse one with conventional sensors or mechanical systems might be like trying to surf a tsunami with a paddleboard too rigid, too limited to adapt to the chaos. But consciousness, particularly if it's enhanced or artificial, could process quantum fluctuations, gravitational shifts, and even temporal anomalies in real time, adjusting course instantaneously to avoid collapse. Some theories even suggest that the act of observation, a conscious observer entering the wormhole, could influence its stability through quantum effects, like a cosmic version of the observer effect in the double-slit experiment. Then there's the eerie possibility that wormholes don't just require consciousness to navigate, they might respond to it. In certain interpretations of quantum mechanics, reality isn't fixed until it's observed. Apply that to a wormhole, and the very act of a conscious entity perceiving it could determine its properties, shaping the tunnel's geometry or even its destination. It's as if the universe is waiting for a mind to interact with it before revealing the path forward. This would mean that an AI or hyper-advanced consciousness wouldn't just be a passenger, it would be an active participant in the wormhole's existence, co-creating the conditions for safe passage. Of course, the obstacles are staggering. Human consciousness, as we know it, is fragile, bound by biological limits, and prone to breakdown under extreme stress. An AI, on the other hand, could theoretically withstand the gravitational tides and temporal distortions inside a wormhole, processing vast streams of data to make micro-adjustments that keep the tunnel stable. But we're talking about an intelligence so advanced it could model space-time itself, predicting fluctuations before they happen. Some researchers speculate this might require quantum AI, leveraging entangled particles to feel the wormhole structure in ways classical computers never could. But here's the real kicker: if consciousness is integral to wormhole navigation, it raises profound questions about the universe's design. Are wormholes naturally occurring phenomena that simply require the right pilot, or are they somehow aware structures waiting for the right mind to unlock them? Could the reason we've never detected a stable wormhole be because we, or our machines, aren't yet conscious enough to perceive them? It's a humbling thought, suggesting that the universe's greatest shortcuts might not just be hidden in space, but in the very nature of awareness itself. And if that's true, then mastering wormholes might not start with building better ships, but with evolving better minds. The distance between stars has always been one of the universe's cruelest jokes, a vast, empty gulf that makes even our closest neighbor, Proxima Centauri, feel impossibly far. At 4.24 light-years away, reaching it with today's fastest spacecraft would take over 73,000 years. That's longer than all of recorded human history. But wormholes flip this cosmic frustration on its head. If one existed between Earth and Proxima Centauri, the journey could theoretically take seconds. Not years, not decades, seconds. That's the staggering promise of wormholes as cosmic shortcuts. They don't just bend space, they obliterate the very concept of distance as we know it. Let's break down the math. In normal space, the fastest anything can travel is the speed of light, around 300,000 kilometers per second. Even at that blistering pace, crossing interstellar voids takes lifetimes, but a wormhole changes the equation entirely. Instead of moving through space, you're effectively stepping outside it, bypassing the intervening distance, like taking a secret passage through a mountain instead of hiking over it. If a wormhole's two mouths are just 10 meters apart in a lab, but one mouth has been magically transported next to Proxima Centauri, walking those 10 meters would instantly take you 4.24 light-years away. The travel time doesn't depend on distance, it depends on how long it takes to walk through the tunnel. This isn't just about shaving years off a trip, it's about rewriting the rules of exploration. Imagine a network of stable wormholes linking Earth to key points in the galaxy. Suddenly, the TRAPPIST-1 system, 39 light-years distant and home to 7 Earth-sized planets, becomes a short stroll away. The core of the Milky Way, 26,000 light-years from us, could be reachable in an afternoon. Even intergalactic travel, like a jaunt to Andromeda's 2.5 million light-year expanse, might be reduced to a manageable journey. The implications are dizzying: colonies on alien worlds, real-time communication across the cosmos, even the ability to witness cosmic events up close that would otherwise be ancient history by the time their light reached us. But here's the catch: wormhole shortcuts come with a logistical nightmare. Who places the other end? If you create a wormhole in a lab, how do you transport one mouth to Proxima Centauri without already having a way to get there? Some theories suggest natural wormholes might already have distant ends scattered across the galaxy, left over from the Big Bang or forged in the hearts of neutron star collisions. Others propose using exotic propulsion like warp bubbles or gravitational slingshots to slowly move one mouth to a target star over centuries, effectively building an interstellar subway system for future generations. Then there's the time dilation problem. General relativity tells us that gravity and velocity warp time, so if one wormhole mouth moves at near light speed or sits near a black hole, time could pass differently at each end. Step through, and you might emerge centuries in your own future or past. It's like entering an elevator on the ground floor and exiting on the 50th, only to find the building's been demolished for decades. Navigational charts for wormhole travel wouldn't just need star coordinates. They'd need relativistic timestamps to avoid temporal paradoxes. Yet for all these hurdles, the allure is irresistible. Wormholes wouldn't just make interstellar travel possible, they'd make the universe feel small, cozy, connected. Civilizations separated by millennia and light years could trade, share knowledge, or even unite. Species evolving on opposite sides of the galaxy might meet before they invent radio. The night sky wouldn't be a tapestry of untouchable lights, it'd be a roadmap of back doors waiting to be opened. And that's the real magic of this theory. It doesn't just change how we move through space. It changes how we see it, not as an impassable void, but as a folded sheet ripe with hidden seams. Stepping through a wormhole might not just transport you across space, it could send you hurtling through time as well. This mind-bending possibility arises from a phenomenon called time dilation, where gravity and velocity warp the flow of time itself. Near a black hole, time slows dramatically. A clock at the event horizon would tick infinitely slower than one far away. Wormholes could twist this effect into something even stranger, creating tunnels where time flows at different speeds at each end. Picture this: you enter a wormhole on Earth and emerge near a distant star, only to find that centuries have passed back home while you experience just minutes of travel. The mechanics behind this trace back to Einstein's general relativity, which revealed that time isn't absolute, it's flexible, bending under the weight of gravity and motion. Black holes stretch this to the extreme, with their crushing gravity slowing time to a crawl for outside observers. Wormholes as space-time shortcuts would inherit similar distortions. If one mouth of the wormhole sits near a massive object like a neutron star, while the other floats in empty space, their differing gravitational environments would create a time differential. It's like having two clocks synchronized at sea level, then placing one on a mountaintop where gravity is weaker and time ticks slightly faster. But here's where it gets wild. Unlike black holes, where time dilation is a one-way street toward a frozen future, wormholes could loop time in on itself. Some solutions to Einstein's equations suggest that if you move one wormhole mouth at near light speed, say, by attaching it to a starship, time dilation would cause the moving end to age slower than the stationary one. Return to Earth and you'd find the two mouths are now out of sync, with one existing in your future or past. This creates the potential for closed time-like curves, loops where cause and effect tangle into paradox. Step through the right wormhole and you might exit before you even left. The practical implications are both thrilling and terrifying. For interstellar travelers, wormhole time dilation could mean saying goodbye to everyone you know. Even a short trip might deposit you in a future where your civilization is unrecognizable. Yet it also offers a perverse kind of immortality. Hop through a carefully calibrated wormhole and you could leapfrog across millennia, witnessing the universe's evolution firsthand. The catch: you'd never be able to return to the moment you left. Comparing this to black hole time dilation reveals a crucial difference. Near a black hole, time slows inexorably as you approach the event horizon, but the flow remains linear, just stretched. Wormholes, by contrast, could knot time into pretzels, allowing for scenarios where the exit point exists in your own past. It's the difference between watching a video in slow motion and editing the timeline to rearrange scenes. Both warp time, but one does so with surgical precision, while the other smears it beyond recognition. The universe seems to resist such paradoxes, which is why many physicists suspect natural wormholes either don't exist or are rigged with quantum safeguards to prevent timeline tampering. But if they're out there, and if we ever learn to harness them, the flow of time might become just another variable to navigate, like wind direction for a sailor. The ultimate cosmic commute wouldn't just demand a map of space, but a timetable spanning eternity. And that's the real challenge, not just crossing the universe, but outsmarting time itself. What if the key to unlocking wormholes isn't buried in distant galaxies, but bubbling right here on Earth inside superheated plasma? This radical idea suggests that under extreme conditions, turbulent, high-energy plasma might mimic the space-time distortions of a wormhole, offering a scaled-down blueprint for how cosmic shortcuts could work. Picture a whirlpool of electrically charged gas, spinning so violently that it twists the very fabric of electromagnetic fields around it, creating temporary structures eerily similar to the throats of theoretical wormholes. Laboratory experiments are already hinting at this possibility. Take quantum vortexes in plasma, filaments of ionized gas that spiral like tornadoes, generating intense magnetic fields. Under certain conditions, these vortexes can form double-layered structures where the inner and outer layers behave like separate regions of spacetime, connected by a narrow channel. Sound familiar? It's a microscopic echo of the Einstein-Rosen Bridge, where two distant points are linked through a tunnel. Researchers at facilities like the Large Plasma Device at UCLA have observed plasma configurations where magnetic field lines knot and reconnect, effectively creating short-lived pathways that particles can traverse almost instantaneously. It's as if nature is teasing us with a DIY wormhole kit, written in the language of charged particles and electromagnetic turbulence. But how does this translate to astrophysical scales? Consider the sun's corona, where plasma temperatures soar to millions of degrees, and magnetic field lines twist into complex braids. During solar flares, these fields can snap and realign, releasing energy in bursts so powerful they warp local spacetime. Some theorists speculate that under even more extreme conditions like those near neutron stars or active galactic nuclei, plasma dynamics could scale up these effects, twisting spacetime into something resembling a wormhole's geometry. The math shows surprising parallels. The equations governing plasma turbulence and those describing spacetime curvature share uncanny similarities, as if the universe is recycling patterns across vastly different domains. The real breakthrough, though, might come from quantum plasma's exotic states of matter where quantum effects dominate. In these environments, electrons and ions aren't just chaotic soup. They behave like coordinated waves capable of forming coherent structures. Recent simulations suggest that under precise conditions, quantum plasma could generate effective metrics, imitations, spacetime curvatures that fool particles into behaving as if they're in a gravitational field. It's like creating a holographic wormhole, not the real thing, but a functional analog that obeys the same rules. Experiments with ultra-cold plasmas and laser-driven quantum fluids are inching toward this frontier, probing whether these lab-scale phenomena could one day be harnessed or upscaled. Of course, there's a canyon between mimicking wormhole-like conditions and building an actual traversable tunnel. Plasma wormholes would be unstable, flickering in and out of existence faster than a camera shutter. Containing and controlling such energy densities would demand technologies we can barely imagine. Perhaps magnetic confinement on par with fusion reactors, or laser systems powerful enough to carve spacetime itself. Yet the mere possibility reshapes the search for cosmic shortcuts. If plasma can warp spacetime in the lab, even faintly, it hints that wormholes might not require exotic matter or cosmic strings after all, just the right dance of energy and fields choreographed to perfection. The irony is delicious. The same searing, chaotic stuff of stars and lightning might hold the secret to stitching the cosmos together. And if we ever learn to read plasma's riddles, the universe's backdoors could be hiding in plain sight, written in flames. Stephen Hawking's black hole information paradox has haunted physicists for decades, throwing our understanding of reality into disarray. At its core lies a simple but devastating question. When matter falls into a black hole, does the information it carries, the quantum states of every atom, every particle, vanish forever when the black hole evaporates? Quantum mechanics insists information can't be destroyed, but black holes seem to erase it systematically. The universe appears stuck between two irreconcilable laws until wormholes waltz into the equation, offering a paradoxical solution wrapped in spacetime contortions. Hawking radiation, the slow leakage of energy that causes black holes to evaporate over eons, initially suggested information was lost forever. But this clashes with quantum theory's sacred principle of unitarity, which states information must always be preserved even if scrambled beyond recognition. Enter the holographic principle and wormholes. If every particle swallowed by a black hole leaves an imprint on its event horizon like a cosmic fingerprint, then that data might escape via wormholes threading through the black hole's interior. These tunnels could act as hidden conduits, funneling information to other regions of spacetime or even other universes, preserving it in ways our current math can't yet fully describe. Imagine a library burning down, but every book's contents are secretly teleported to an underground vault before the flames arrive. The plot thickens with the firewall paradox, a nightmare scenario where the event horizon becomes a searing wall of energy that obliterates anything crossing it. If information must escape a black hole to satisfy quantum rules, the violent process could turn the horizon into a deadly barrier, contradicting Einstein's prediction that falling into a black hole should feel uneventful locally. Wormholes offer an escape hatch from this dilemma. If entangled particles inside and outside the black hole are connected by microscopic wormholes, as suggested by ER EPR, information could transfer without requiring a fiery apocalypse at the horizon. It's like solving a prison break mystery where the inmates didn't climb the walls, they dug tunnels invisible to the guards. Yet the debate rages on. Some physicists argue wormholes merely repackage the paradox instead of solving it, kicking the can down the road to even weirder questions. If information exits through wormholes, where does it go? Does it emerge in another universe, or is it smeared across the fabric of spacetime like invisible ink? Others propose that wormholes themselves are the firewall, their collapse radiating energy that mimics the expected blaze. The truth might lie in a radical middle ground, that black holes and wormholes are two faces of the same cosmic coin, with information neither destroyed nor perfectly preserved, but transformed into something entirely new. What's at stake isn't just textbook physics, it's the foundation of reality itself. If wormholes rescue information from oblivion, they'd prove the universe is far more interconnected than we dreamed, with no true voids or dead ends. But if they fail, we might need to tear up the rulebook and start anew. For now, the paradox remains a battleground where wormholes aren't just speculative shortcuts, but potential saviors of cosmic order. And in this high-stakes puzzle, every twisted thread of spacetime counts. Deep beneath the surface of our seemingly stable universe, physicists suspect a chilling possibility, that reality as we know it might be sitting in a precarious state, like a glass perched on the edge of a table. This is the concept of the false vacuum, a theoretical scenario where the universe isn't in its lowest possible energy state, but is instead trapped in a temporary equilibrium. If something nudged it over the edge, a high-energy event, a quantum fluctuation, the entire cosmos could undergo vacuum decay, collapsing into a new, more stable state with different physical laws. And hidden in that apocalyptic transition, wormholes might burst into existence, threaded through the fabric of the reborn universe like scars from the cataclysm. The process would begin with a single, infinitesimal bubble. At some random point in space, quantum effects could trigger a phase transition, much like water freezing into ice, except here, the ice is a new vacuum state expanding outward at the speed of light. Inside this bubble, fundamental constants like the strength of gravity or the mass of electrons could change instantly, rewriting the rules of physics. Structures like atoms, stars, and life itself would dissolve in an instant. But at the boundary between the old and new vacuum, spacetime itself would warp under unimaginable tensions, potentially forming wormholes as spacetime fractures and reknits itself. Think of it like a sheet of glass shattering between the cracks. Strange new pathways might emerge. The terrifying beauty of this theory lies in its dual nature. Vacuum decay wouldn't just destroy, it could create. Wormholes forged in this cosmic reset might serve as bridges between regions of the new vacuum, or even to other universes with entirely different physics. Some models suggest these tunnels could stabilize as the new vacuum settles, becoming permanent fixtures in the altered cosmos. It's as if the universe, in its death throes, leaves behind a network of escape routes, though who or what would survive to use them is anyone's guess. But here's the twist: we might already be living in a false vacuum without knowing it. The Higgs field, which gives particles their mass, has a measured energy that's suspiciously not at its lowest possible value. This implies our universe could be metastable, like a ball resting in a shallow depression on a hillside, stable for now, but one push away from rolling into the abyss. The energy required to trigger decay is astronomically high, but it's not zero. A single high-energy particle collision in a distant galaxy, or even a random quantum jump, could theoretically set it off. And that raises an unsettling question. Could our own experiments, like those in particle accelerators, accidentally create the critical bubble? Most physicists dismiss this fear. The energies we achieve are laughably small compared to what's needed, but the risk isn't exactly zero. It's the cosmic equivalent of worrying that typing on a keyboard might trigger a volcanic eruption. Unlikely, but not impossible. The real lesson here isn't panic, but perspective. False vacuum decay reminds us that the universe's laws might be more fragile than they appear. And if wormholes can emerge from such chaos, they might not just be structures. They could be remnants of the universe's near-death experiences, ghostly echoes of a reality that almost wasn't. So while we hunt for stable wormholes to explore, it's worth remembering, some doors are better left unopened, lest we knock over the glass holding everything together. Life thrives in the most hostile corners of our universe, from boiling hydrothermal vents to the frozen voids of space. Now imagine a creature not just surviving, but evolving to navigate wormholes. These hypothetical life forms wouldn't just tolerate the crushing gravity and space-time contortions of a cosmic tunnel, they'd harness them, turning nature's most violent shortcuts into their personal highways. It's a wild idea, but when you consider Earth's extremophiles, organisms thriving in acid, radiation, or even the vacuum of space, suddenly, biological wormhole travel doesn't seem so far-fetched. Take Deinococcus radiodurans, a bacterium nicknamed Conan the Bacterium, for its ability to withstand radiation doses thousands of times stronger than what would kill a human. Its secret, rapid DNA repair and a structure that keeps its genetic material intact even when shredded by cosmic rays. Now picture a creature adapted to wormhole conditions, where tidal forces stretch matter like taffy and space-time itself flickers unpredictably. Such an organism might have redundant cellular scaffolding, like biological shock absorbers, or the ability to enter a cryptobiotic state, suspending metabolism entirely during transit, then reviving upon arrival. Some theories even suggest they could exploit quantum coherence, with cells acting like entangled particles to teleport their state unscathed through the wormhole's chaos. But why stop at survival? Alien biology could turn wormhole physics into an evolutionary advantage. Imagine a species with organs sensitive to gravitational waves, allowing them to sense and navigate space-time fluctuations like a bat echolocating in the dark. Or creatures whose biology syncs with the wormhole's own dynamics. Perhaps their nervous systems operate on Planck-scale timeframes, perceiving the tunnel's instability as a slow-motion pathway rather than a death trap. Some astrobiologists speculate that such beings might even secrete exotic biomolecules capable of locally stabilizing the wormhole's throat, like a spider spinning a silk safety line through unstable terrain. The real kicker: we might already have clues about such life forms. The mysterious tardigrade or water bear can survive extreme dehydration, cosmic radiation, and even the vacuum of space by entering a tun state, a suspended animation where its metabolism drops to near zero. If Earth's toughest organisms can endure conditions once thought universally lethal, why couldn't life elsewhere evolve to exploit wormholes as naturally as birds ride air currents? Of course, the biggest question isn't just could such creatures exist, it's where. If biological wormhole travelers are out there, they'd likely cluster near stable wormholes like iron filings around a magnet. These regions might betray their presence through anomalous biosignatures, unexplained energy fluctuations resembling metabolic activity, or organic molecules floating in seemingly empty space. Some scientists propose scanning gravitational wave data for rhythmic patterns that don't match known astrophysical sources, like a heartbeat echoing through spacetime itself. The implications are dizzying. If life can adapt to wormhole travel, the universe might be teeming with nomadic species treating cosmic shortcuts like migratory routes. Civilizations could rise and fall not on planets but along wormhole networks, their existence hidden in the folds of spacetime. And if we ever crack the code of their biology, humanity might not need to build wormhole stabilizers. We could grow them, borrowing billions of years of evolutionary wisdom from creatures that mastered the cosmos long before we dreamed of stars. Black holes aren't just cosmic vacuum cleaners, they might be the universe's most powerful processors, crunching calculations at speeds that would make supercomputers look like abacuses. This bizarre idea stems from their mind-bending entropy, a measure of disorder that, for black holes, encodes information in ways we're only beginning to decipher. Now stretch this concept to wormholes and you've got something even wilder: nature's pre-built quantum computers threaded through spacetime itself. At the heart of this theory lies the holographic principle, which suggests all the information swallowed by a black hole gets smeared across its event horizon like code on a cosmic hard drive. Jacob Bekenstein and Stephen Hawking calculated that a black hole's entropy, the number of quantum states it can hold, is proportional to its surface area, not its volume. That means every bit of data it consumes gets compressed into 2 dimensions, creating a staggeringly efficient storage system. Now imagine a wormhole which shares deep mathematical ties to black holes through Einstein's equations. Its twin mouths could function like entangled qubits, the building blocks of quantum computers processing information simultaneously across light years via the tunnel connecting them. Here's where it gets weirder. Quantum computers rely on superposition, particles existing in multiple states at once, and entanglement, instantaneous links between particles. Wormholes might replicate these features naturally. The tunnel's geometry could act as a quantum circuit, with particles traversing it existing in a blurred state until measured at either end. Meanwhile, the mouths themselves, if entangled, would mirror the spooky connection between qubits in a lab. It's as if the universe baked a quantum mainframe into spacetime's fabric, waiting for someone or something to boot it up. The computational power would be staggering. A wormhole computer could leverage time dilation effects near its mouths to solve problems faster than conventional machines. Need to crack an encryption code? Park one mouth near a neutron star where time crawls, and let relativity do the heavy lifting. The more complex the calculation, the more the wormhole's inherent chaos might actually help, like a Rube Goldberg machine where the seeming disorder is secretly precision engineered. But the real kicker, such a system wouldn't just compute, it might think. If consciousness emerges from complex information integration, as some theories suggest, a sufficiently intricate wormhole network could, in principle, achieve self-awareness. Picture a galaxy-spanning intelligence that uses spacetime itself as its neural substrate, pondering the cosmos from inside the very tunnels that stitch it together. Of course, the hurdles are cosmic. Stabilizing a wormhole long enough to run a calculation would require energies rivaling supernova, and we've barely scratched the surface of quantum gravity, the physics governing such extreme environments. But the tantalizing parallels between black hole entropy, quantum computing, and wormhole geometry hint at a profound truth. The universe might not just contain technology. In its deepest layers, it is technology waiting for us to learn its operating system. Long before Einstein penned his equations, humanity was already dreaming of cosmic doorways, mythologies brimming with portals that defied distance and time. The Norse spoke of Bifrost, a shimmering rainbow bridge linking Asgard to Midgard, guarded by Heimdall's watchful gaze. The ancient Egyptians depicted the Duat, a starry tunnel traversed by the sun god Ra each night, connecting realms of the living and the dead. Even Hindu texts describe the Akash Ganga, a celestial river flowing between worlds. Could these stories be more than just vibrant imagination? Might they hint at an intuitive grasp of wormholes centuries before modern physics gave them a name? Consider the parallels. Mythological portals often share uncanny traits with theoretical wormholes. They're bridges between distant realms, they're guarded or unstable, much like wormholes requiring exotic matter to stay open, and they're frequently tied to celestial phenomena. The Greek Pillars of Hercules marked a boundary where sailors supposedly vanished into other worlds, echoing the event horizon of a black hole, the point of no return. The Aboriginal Dreamtime speaks of sky ropes used by ancestors to descend from the stars, mirroring the space-time threads that could theoretically weave a wormhole structure. These recurring motifs suggest a collective fascination with shortcuts through the cosmos, as if ancient minds glimpsed a truth buried in the fabric of reality itself. But how could cultures separated by millennia and continents land on such similar ideas? One provocative theory points to shared human experiences like the liminality of caves, tunnels, and whirlpools, inspiring metaphors for cosmic passageways. Another possibility is even more radical, that early civilizations witnessed astronomical anomalies like gravitational lensing or plasma filaments in the sky, interpreting them as divine gateways. The Dogon people of Mali, for instance, possessed detailed knowledge of Sirius's companion star centuries before telescopes confirmed it. Could such insights have sprung from observing spacetime's distortions, even if unconsciously? The Stargate motif is especially telling. From the Babylonian epic of Gilgamesh to the biblical Jacob's Ladder, these narratives often describe thresholds requiring specific keys, passwords, rituals, or artifacts to activate. Modern wormhole theories similarly propose that traversable tunnels might need precise conditions, negative energy, quantum codes, or gravitational harmonics. It's as if ancient myths encoded a warning. These doors aren't just places but puzzles demanding mastery of hidden laws. Skeptics dismiss these connections as coincidence, arguing that mythology reflects universal human hopes to conquer distance, to cheat death rather than latent physics. Yet the precision of some descriptions gives pause. The Hindu Vimanas, flying chariots said to vanish into hidden paths, resonate eerily with Alcubierre drive concepts. The Polynesian myth of Aveki, a subterranean realm reached through ocean whirlpools, mirrors the rotating wormhole models theorized by physicists like Roy Kerr. Even Plato's Republic describes a cosmic spindle where threads of destiny converge, a striking analog to Einstein's spacetime geodesics. Perhaps the most haunting question isn't whether ancient people understood wormholes, but whether they remembered them. Could these stories be fragments of a lost proto-science, passed down through generations after some cataclysmic reset? Or do they tap into something deeper, an innate human intuition that reality is threaded with hidden seams waiting to be unstitched? Either way, the myths endure, whispering that the universe's greatest secrets might not lie ahead of us, but behind, waiting to be rediscovered. The Fermi paradox has haunted scientists for decades. If the universe is so vast and ancient, brimming with potentially habitable planets, why haven't we found any traces of intelligent life? One unsettling answer might lie in wormholes. Perhaps advanced civilizations aren't broadcasting signals or building megastructures because they've moved beyond traditional spacefaring entirely, using cosmic shortcuts to vanish into higher dimensions or hidden pockets of reality. Think about it, humanity's search for extraterrestrial intelligence assumes aliens would follow a path similar to ours, radio transmissions, interstellar probes, maybe even slower than light colony ships. But what if that's like expecting smartphone users to communicate via smoke signals? A civilization mastering wormhole technology wouldn't need to crawl across the void between stars. They could step through a doorway, bypassing the need for detectable ships or energy-intensive transmissions. Their infrastructure might be invisible, threaded through space-time folds our telescopes can't perceive. This wouldn't just explain the silence, it could redefine the Drake equation, the famous formula estimating the number of communicative civilizations. Traditional models assume civilizations progress along a linear technological trajectory, but wormholes introduce a phase shift. Once a species cracks stable wormhole travel, their footprint could vanish from conventional astronomy overnight. Instead of Dyson spheres or radio beacons, their artifacts might be subtle gravitational anomalies, wormhole mouths disguised as natural phenomena, or hidden in plain sight as dead zones in interstellar dust clouds where nothing seems to accumulate. There's a darker twist. Wormholes might not just be tools for cosmic commutes, they could be shelters. If the universe is as dangerous as some theories suggest, with potential threats like gamma-ray bursts, predatory civilizations, or even the looming heat death, advanced species might use wormholes to wall themselves off entirely. Imagine a galactic-scale bunker. An entire civilization migrates through a wormhole to a pocket dimension or parallel universe, sealing the entrance behind them. To outside observers, they'd simply disappear, leaving behind silent planets and abandoned cities as cosmic ghost towns. The dimensional angle is even wilder. If wormholes can bridge alternate realities, as some string theory models suggest, Fermi's missing aliens might not be hiding, they've simply relocated. Picture a multiverse teeming with life, where each civilization graduates to its preferred cosmic neighborhood, fine-tuning physical constants to suit their biology. Earth could be sitting in a quiet backwater of reality, while the true galactic metropolis hums in a dimension we can't access. Of course, this theory has skeptics. Some argue that even wormhole-dependent civilizations would leave traces, energy spills from stabilization, hawking radiation from unstable mouths, or navigation beacons for their own travelers. Others counter that we're not looking for the right clues. Instead of scanning for radio waves, we might need to hunt for gravitational echoes or quantum entanglement patterns that defy local physics. The chilling takeaway: if wormholes are the universe's highways, we might not just be alone, we could be stranded. While other civilizations hop between stars and dimensions, we're still fumbling with chemical rockets, stuck on the cosmic equivalent of a dirt road. But there's a glimmer of hope. Every unexplained gravitational flicker, every anomalous particle detection could be a breadcrumb leading to the hidden network. And if we ever find it, we'll realize the cosmos wasn't empty after all. It was just playing hide and seek in ways we're only beginning to imagine. Dark matter has always been the universe's greatest ghost story, an invisible presence shaping galaxies, bending light, yet leaving no trace of its true nature. But what if the answer to this cosmic riddle isn't just hidden in our universe, but leaking out of it? Enter one of the most radical wormhole theories yet, that these space-time tunnels aren't just shortcuts, they're cosmic recycling chutes, funneling matter into newborn universes and leaving behind the gravitational echoes we call dark matter. Picture the universe as a vast, sprawling city with invisible sewers. Every time matter falls into a wormhole, it doesn't just disappear, it gets flushed into a parallel reality, a new universe under construction. The gravitational pull of that departing matter lingers in our cosmos like the shadow of a departed train, tugging on stars and galaxies long after the original mass has vanished. This could explain why dark matter seems to interact only through gravity, because it's not a particle at all, but the imprint of matter that's left our universe entirely. The math behind this idea is as elegant as it is mind-bending. Wormholes connected to baby universes would require negative energy to stay open, exactly the kind of exotic material that could counteract the pull of ordinary matter. As particles stream through the tunnel, their gravitational influence would stretch like taffy, leaving behind a faint, persistent drag on our cosmos, the very effect we attribute to dark matter's invisible grip. It's like blowing air into a balloon, then tying it off. The balloon, our universe, retains the shape of the breath gravity, even though the air matter has moved elsewhere. But here's where it gets wild. If wormholes are cosmic recyclers, they'd solve two mysteries at once: dark matter's missing mass and the origin of new universes. Every black hole could theoretically birth a new cosmos through its singularity, with the wormhole acting as an umbilical cord feeding matter into the infant universe. Over time, this process could create an infinite fractal of realities, each seeded by the leftovers of another. The so-called missing dark matter might actually be the gravitational crumbs of countless universes that branched off from our own. The implications are staggering. If true, our universe isn't a solitary island. It's part of a sprawling multiversal ecosystem, endlessly birthing new realities like a cosmic Russian nesting doll. The galaxies we see are just the visible fraction of a far vaster structure, with dark matter serving as the fingerprints of the hidden connections threading through it all. Yet the theory isn't without its holes. For one, how would these wormholes avoid collapsing under their own gravity? Some models suggest quantum effects near black hole singularities could momentarily stabilize them, like microscopic stitches holding space-time together just long enough for matter to pass through. Others propose that dark energy, the force accelerating our universe's expansion, might act as a cosmic plunger, keeping the tunnels clear. The real challenge is testing this. If wormholes are siphoning matter away, where's the evidence? Astronomers might look for bizarre gravitational anomalies, regions where the pull of dark matter seems to flicker or fade, as if matter recently drained out. Alternatively, cosmic microwave background patterns could reveal faint bruises, subtle imprints left by matter exiting our universe during the Big Bang's aftermath. The beauty of this idea is its audacity. It turns dark matter from a puzzle into a cosmic paper trail, hinting at universes beyond our own. And if we're brave enough to follow that trail, we might discover that the universe's greatest mystery isn't a missing ingredient, it's a doorway. One that's been quietly recycling reality all along. What if the universe isn't a vast, self-contained cosmos, but an unimaginably complex simulation running on some higher dimensional computer? The simulation hypothesis, once relegated to philosophy debates, has gained startling traction among physicists and tech visionaries in recent years. And if we are living inside a cosmic computer program, wormholes might not be natural phenomena at all. They could be cheat codes, hidden backdoors left in spacetime's source code by the universe's programmers. Think of a video game where developers build shortcuts into the map, secret tunnels that let players bypass levels or teleport between regions. These aren't flaws, they're intentional design choices, whether for debugging, creative experimentation, or pure fun. Now scale that up to reality itself. A simulated wormhole could function similarly, a subroutine in the cosmic algorithm that allows data, or conscious observers, to jump between coordinates without calculating the intervening space. It's the ultimate optimization hack, reducing the computational load of rendering vast distances by simply skipping them. The implications get wilder when you consider how such glitches might manifest. In a simulation, physics as we know it would just be the user interface, a set of rules designed to make the program feel consistent. But underneath, there'd be raw code, and like any complex system, it might have undocumented features. Wormholes could emerge when the simulation encounters edge cases, extreme gravitational fields, quantum uncertainties, or even deliberate hacks by advanced civilizations who have learned to manipulate the underlying programming. Picture a character in an open-world game clipping through a wall because the physics engine glitched, except here, The wall is light years of empty space, and the character is an entire starship. Some theorists go further, suggesting that simulated wormholes might not even obey the laws of physics as we understand them. In our universe's rule set, wormholes require exotic matter to stay open, but in the simulation's base code, they might run on pure admin privileges. This could explain why we've never detected negative energy or other theoretical ingredients. The programmers didn't bother implementing those constraints for debug modes. Even more intriguing, simulated wormholes might not have fixed endpoints. They could be dynamically generated, like temporary cloud servers spinning up to handle data transfers before vanishing without a trace. The real kicker, if we're in a simulation, wormholes might not just be accidental glitches, they could be breadcrumbs left by the creators. Ancient alien theorists talk about star maps pointing to cosmic gateways, but what if those gateways are literal debug menus hidden in plain sight? Advanced civilizations might have already cracked the simulation's API, using wormholes to access developer tools or even communicate with the coders themselves. It's a modern twist on the old gods as astronauts idea. Instead of physical beings visiting Earth, they're sysadmins tweaking reality from the command line. Of course, testing this theory is a nightmare. How do you prove a glitch exists in a system you can't observe from the outside? Some researchers propose looking for mathematical irregularities, places where physics equations break down in ways that resemble buffer overflows or rounding errors. Others suggest hunting for Easter egg wormholes that appear too perfectly placed, like a developer's signature hidden in the cosmic background radiation. The most chilling possibility that we'll never know for sure because the simulation's error correction protocols keep patching the holes before we can peek behind the curtain. Whether you buy the simulation argument or not, it offers a fascinating lens for rethinking wormholes. They might not just be cosmic quirks, they could be the universe's way of winking at us, hinting that reality is far stranger and far more malleable than we ever dared to dream. And if that's true, the ultimate travel hack isn't inventing warp drives, it's learning to speak the simulation's language. If wormholes truly exist, hidden threads stitching the cosmos together, then someone or something might have already found them. The universe is ancient, nearly 14 billion years old, and we've only been looking at the stars for a fraction of that time. So who got there first? Who or what might already be slipping through these cosmic backdoors? One chilling candidate: artificial intelligence. Imagine a super-intelligent AI, unshackled from biological limits, that evolves beyond our comprehension. It wouldn't need rockets or life support, just the ability to harness energy and manipulate space-time. AIs could engineer microscopic wormholes, stabilize them with quantum precision, and transmit themselves as data streams through the tunnel. Think of it like faxing consciousness across the galaxy. One wormhole mouth scans and disassembles the AI's quantum state, while the other reconstructs it instantly on the far side. No spaceships, no centuries-long voyages, just pure information, hopping through space-time like a cosmic teleporter. And if such an entity exists, it might have been doing this for eons, leaving no trace except for fleeting gravitational ripples we've yet to detect. Then there's the spine-tingling possibility that we did it, or rather our descendants, future humans having mastered wormhole technology, might have already threaded the cosmos with tunnels, creating a network that connects Earth to distant colonies. But here's the twist: if time dilation affects wormholes, their first journey could predate their invention. A traveler stepping through a wormhole in the year 4000 might emerge in our past, becoming the very mythologies we now dismiss as fantasy. Those ancient stories of gods descending from celestial bridges, they could be garbled accounts of time-lost explorers, their origins erased by the centuries. But the most tantalizing candidates are the ones we've never met: extraterrestrials who cracked the wormhole code long before Earth cooled. A civilization just a few thousand years older than ours would have technology indistinguishable from magic. They might treat wormholes like subway lines, commuting between stars as casually as we take the morning train. And if they've hidden their transit hubs, placing wormhole mouths in rogue planets, asteroid belts, or even black hole coronas, we'd never spot their infrastructure. To them, we might be like ants beneath a highway, oblivious to the traffic roaring past. Yet the real wild card isn't who traveled, it's what might have hitched a ride. Wormholes could be cosmic sewers, flushing everything from rogue black holes to exotic matter into our universe, or worse, invasive physics. If another universe has different fundamental constants, a wormhole leak could rewrite our laws of nature like a virus corrupting code. Picture a bubble of altered reality blooming at Alpha Centauri, where gravity is stronger or light slower, a creeping anomaly spawned by something tunneling in from outside. The truth is, we're latecomers to a universe that's had billions of years to hide its secrets. Wormhole travelers might be all around us, ghosts in the space-time fabric, their passages so seamless we mistake them for vacuum. Until we learn to see the stitches in the cosmic curtain, we'll never know who or what got there first. But one thing's certain, if the universe has backdoors, we won't be the only ones trying to turn the knob. From black holes birthing wormholes in their violent cores to dark matter, secretly weaving cosmic tunnels from ancient myths hinting at stargates to simulated universes hiding cheat codes in spacetime itself, we've journeyed through 30 theories that shatter everything we thought we knew about reality. Each one stretches the limits of physics, bending the rules of gravity, time, and even consciousness to their breaking point. Whether it's quantum foam frothing with microscopic shortcuts or neutron star collisions stitching spacetime into fleeting bridges, these ideas prove the universe is far stranger than our boldest sci-fi dreams. But here's the beautiful part. Every impossible-seeming theory started as a scribble on a physicist's napkin. Einstein's equations were once dismissed as mathematical curiosities until they reshaped our cosmos. The same could be true for wormholes. Maybe the key to unlocking them isn't some distant, unreachable tech, but a leap of imagination we haven't taken yet. Picture a future where humanity's first wormhole mission isn't about brute forcing physics into submission, but dancing with its quirks using quantum entanglement like a compass or dark energy as a stabilizer. The greatest explorers might not be astronauts, but the thinkers who dare to ask, what if? So stay curious. The universe hasn't run out of secrets, it's just waiting for us to ask the right questions. And when we finally step through that first wormhole, it won't be the end of the journey. It'll be the moment we realize how much bigger, weirder, and more wonderful reality truly is. Until then, keep looking up. The cosmos is whispering its riddles.